In the previous lessons, we've spoken extensively about chemical reactions, spoken about rates of chemical reactions, spoken about chemical equilibriums, where the rate of the forward reaction equals the rate of the reverse reactions, right? And we've spoken about a number of factors that actually influences equilibrium, right? And in this lesson, we're going to talk about something we call the equilibrium's constant. The equilibrium can be an equilibrium constant, right? And I want us to start off here where we say we have a typical reaction. So this would A would just small letter A would just be the coefficient, maybe B. So these are our reactants. These are just maybe it can be 2A, sometimes it can be 3A, it doesn't matter what it is, right? So it's a reversible reaction we show by those two arrows. So it means that reactants can produces products, but products can also be converted back into reactants. So this is big letter C, right? Cool. So like I mentioned, A, B are reactants, C and D are your products, right? And then A, B, C, and D are coefficients from a balanced equation. So remember, when you balance an equation, you normally put a 2 somewhere, a 3 somewhere, so that your equation is balanced, right? And we've spoken about an equilibrium and what it is. It's when the rate of the forward reaction equals the rate of the reverse reaction. So now I want us to define what do we mean when we talk about an equilibrium constant, right? In a simple way, an equilibrium constant actually refers to it's a ratio between the concentration of products and reactants in a chemical reaction, right? So we're still considering this. So if we had to define the equilibrium constant for this reaction, we would say, okay, we know it's a ratio, it means we're dividing. So it's the ratio of the product, concentration of the product. So that what type of bracket is this? A square bracket. This means we are concerned with the concentration. That's why we put it in the bracket. So we say C D A B. So remember, A and B are our reactants. However, we're not done. We also have to put these coefficients A, B, and C, D. We'll put them there as exponents. So we might have C there, D there. What's this? A, and then B, right? So where A, B, C, D, all of which are in square brackets, are a concentration of each substance available at or present at equilibrium. So it's the concentration at equilibrium. So meaning when we calculate what is this? I'm starting to become forgetful again because I'm a bit tired, right? So remember, Casey, we said it's the product, it's the ratio of the concentration of the product as well as to the concentration of reactants in a chemical reaction at equilibrium. Cool, right? So an important thing that I want you to know is that when we write this equation over here for any sort of reaction, we leave out reactants or products that are either liquids or solids, and you'll see shortly now when we take an example, right? So like I mentioned, let's just take a quick example. So we have ourselves a question here, an example. It says to us, for the reaction where you're reacting sulfur, which is a solid, plus oxygen, which is a gas, it's a reversible reaction from sulfur dioxide, right? Write down here the expression. So we have to write down the expression for the equilibrium constant. And the second question, we have to calculate the equilibrium concentration of oxygen if we are given the equilibrium constant to be 6 and the concentration of sulfur dioxide at equilibrium is 3 mole per cubic decimeters, right? At equilibrium. Cool. So let us just do this question quickly. So what we would do is that, okay, we would look at our reaction. So remember, we say Kc equals to Kc, remember, is the ratio of the reactants over the ratio of our products. the ratio of the products to the reactants. So what is our product here? It's SO2. It's a gas. It means that it is included in the expression. And then what is here, because it's a solid, we don't include this in our expression. We only include gases or aqueous solutions, right? So we would have O2. Cool. And then you check the coefficient of all of them is 1, so you can simply write 1 there. But you remember, if an exponent is 1, you don't necessarily have to write it. So that expression will just be this way. Cool, right? And the second question, they gave us the concentration of this. They've also given us Kc, and we have to find what is the concentration of oxygen. To do that, we'll say, okay, Kc equals to SO2, all of it divided by O2. To make this the subject, we simply cross multiply. So we have that O2. So O2 is just going to be equals to SO2, all of it divided by Kc, right? So the concentration of SO2 will be 3 divided by 6, which is a half. So that it means the concentration of O2 at equilibrium is 0.5 mole per cubic decimeters. And that's your answer. But then, these calculations are normally never this straightforward. Sometimes they are a bit more complicated calculations, and we're going to look at an example of such next. So we have a question over here, and the question says hydrogen and iodine react in the following equation. So we have H2 gas plus I2 gas, which is in a reversible reaction to form hydrogen iodide, right? Which is also a gas. So initially we have 0.496 moles of H2 and 0.18 mole of I2, which are heated at 450 degrees centigrade in a volume of 1 cubic decimeter container, right? And then the equilibrium mixture is found to contain 0.00749 moles of I2. Calculate the equilibrium constant for the reaction. So remember, to calculate the equilibrium constant, we have to know the concentration of all of this at equilibrium. And we are not given that in this instance. In fact, what we're given is just the number of moles initially for reactants, as well as the number of moles of iodine at equilibrium. So how do we go about performing a calculation such as this one? So we're going to use something called the rice method. You'll see why. It involves drawing a table. So in your first column, you have your reaction. Let me just quickly draw it and then I'll explain it. So what we will do is that we will actually draw this table. In the first row, we'll say reaction. So that's our R part, initial number of moles, the change in moles, and then the equilibrium number of moles. So the moles that we start with, the change before we reach to equilibrium, and then finally the equilibrium concentration, right? So our reaction is 1 hydrogen gas plus 1 iodine gas, which gives us 2 hydrogen iodine, right? So let's write the initial number of moles. So remember, at the beginning of your reaction, you have 0.496 moles of hydrogen. You also have 0.181 moles of iodine. But remember, at the beginning, so this is your thing in terms of rate of reaction. So this is the rate, right? Then you have time. At the beginning, so this is your forward reaction. This is your initial number of moles, and then they will drop up until they reach equilibrium. But at the beginning, you don't have any product, so the product is 0, the number of moles. But then it will increase up until it reaches equilibrium, right? Cool. So keep this in mind. And now we will say, okay, what is the change in the number of moles before it reaches equilibrium? So if we started with this and we want to find the equilibrium value, what is that change? And to find it, we'll simply say, okay, we know that it's the number of hydrogen The number of moles of hydrogen starts off as 0.96, and remember this one there is your coefficient is important, and then it decreases by a certain number. Here it's decreasing, and that number we'll call it x. But because the coefficient is 1, we'll simply say it decreases by 1x. And because it decreases, we'll put a negative x. If the value here was 2, we'll say it decreases by 2x. Same thing with iodine. If the reactant is still decreases, we use the coefficient, so it also decreases by the number x, 1x. But this one increases. It starts off at 0, but then it increases up until it reaches that. So it increases by a number 2x. We're using that coefficient. Because it's increasing, we'll say plus. So the number of it is increasing, so we use plus, right? And then we will say, okay, at equilibrium, we know that we will have the number of moles we will have. If we started off with 0.49 and they are decreasing, it means at equilibrium we'll have 0.496 moles minus whatever change of moles we experienced. Same thing, we'll have 0.181 moles minus whatever change that decreases the change. Here it increases, so we'll have 0 plus whatever change that increases 2x, or we can just simply write 2x, right? Cool. So now what do we do? What do you think is the next logical step in terms of us determining, because we want the concentration at equilibrium so that we can calculate the equilibrium's constant. It means that we have to find the value of x. How much is x, and how do you think we're going to do that? So to determine that, you'll have to remember that they mentioned something important in our statement. They said to us that the number of moles, I don't want to write a number there actually. So the number of moles of iodine at equilibrium is 0. Let me check the question statement again. It's 0.00749 moles, right? So we know the number of moles of iodine at equilibrium, right? So if we know that, and it means that also at equilibrium, we also have 0. Let me just drop that. So we also have 0. Now the number of moles is 0.181 minus x. It means I can say that 0.181 minus x equals 0.00749, right? And then it's just a matter of making x the subject. Simple math, you should be able to do it, and you find that x is actually 0.1735 moles, right? So we simply just take the x to the other side and then take this to the other side. It becomes positive this side. We will have 0.181 minus 0.0749, which will give us 0.175. But we're not looking for x. What we're looking for is the concentration. Why is this important? Why is this x important? This x is important because, okay, we found the number of moles. It was given to us. We can say, okay, the number of moles of hydrogen is going to be, we said that at equilibrium is 0.496 minus x. So we have 0.496 minus 0.1735, and you find the value of that to be 0.3225 moles, right? Now we find the number of moles of hydrogen iodide, right? So HI, and we said it's going to just be 2x, meaning it will be 2 multiplied by, we said x is 0.1735, which is if you put that in your calculator, you're gonna come to a value of 0.347 moles. But why was it important for us to actually determine the number of moles? It was important because if we have the number of moles and we were given the volume, they said it's 1 cubic decimeter, it means we can calculate the concentration. So we can calculate the concentration of iodine by simply taking the number of mole there, its number of moles, which is 0. So remember, concentration is given by the number of moles divided by the volume. So it's going to be for I2, for iodine, is going to be 0.00749 divided by 1, which is 0.00749. Concentration of hydrogen is going to be the number of moles of hydrogen, which was 0.3225 divided by the volume, which is 1, which will give me 0.3225, right? So remember, this is measured in mole cubic per cubic decimeters. Mole per cubic decimeters. Do the same thing, concentration for hydrogen iodide. So we have we found that the number of moles to be 0.347, all of it divided by 1 to find the concentration, which means it's 0.347 mole per cubic decimeters, right? So we now have the concentration of all our reactants and products at equilibrium. You can just maybe simply write it back into your table. So we said at equilibrium the number of moles is 0. So that's for hydrogen. No, I'm lying. For iodine, wait, so hydrogen is hydrogen, it's 0.3225. For this one it's 0.00749. For this one it is 0.347. So if we have the concentration, it makes our job much easier. It means we can be able to calculate the Kc, right? Okay, so we have the concentration. This means that we can find Kc. Remember, we can write the expression for Kc to be the ratio of our product, Hi, the ratio of concentration of our products. Because the coefficient is 2, we have to put 2, divided by the ratio of our concentration of our reactants, which is H2 as well as I2. We have the concentration there, we found it to be 0.347, all of it squared divided by 0.00749 multiplied by 0.3225. So it's just a matter of putting this in your calculator. And if you do that, you're going to find your value to be, what is it, 49.85. Doesn't have any units, right? Cool. So to kind of wrap up our discussion, we have to now really ask ourselves a few questions. What does this mean? What does it mean when we have a Kc value that is greater than 1? This means that we actually have more products at equilibrium than reactants, right? So this means we have a high product concentration at equilibrium. Product concentration. And then if Kc somehow it's greater than 0 but it's lesser than 1, it means that we have more reactants than products at equilibrium, meaning we have a high reactant concentration. So this, if we have more products, it means that our reaction will have a very high yield. So we'll produce a lot of product. If we have more reactants, it means we'll have a very low yield, right? So those are a few things that you need to be able to explain with respect to the equilibrium constant.